We're still on with the indices and logarithms playlist, particularly fashioned for people in high school, middle school, junior secondary school, uh, senior secondary school, junior high school, senior high school, people writing SAT, GCSE, IGCSE, and all those kind of exams, like high school related exams like that. So I've been curating this playlist on indices and logarithms all this while. And in the past few videos, I've been talking a lot about solving exponential equations, or what we also know as indicial equations, using different methods like equating indices, like by making the bases the same, using logarithms, factorizing, and so on and so forth. So this is one video in that series of solving exponential or indicial equations. Of course, it doesn't mean that that's the end of the playlist on indices and logarithm. But after now, we'll be shifting to another aspect of indices and logarithms. Okay, so here we're looking at solving exponential models. So the learning outcomes include the following. By the end of this lesson, you should be able to use the exponential growth and decay model, use the half-life model, use the compound interest model, solve exponential equations for time using using logarithms. That is, of course, we are not ready for logarithm. I mean, we are talking about indices and logarithm, and the focus has been on indices for the most part for so far, but gradually we are easing into the whole idea of logarithm because indices and logarithm are complementary. So if you can use exponential equations, if you talk about exponential growth and decay, so populations can grow, populations can decay, whether of humans or even of animals or some particular species. When you talk about half-life, so what comes to mind here is either physics or chemistry, where you talk about radioactive decay. Then use the compound interest model. Of course, that's talking about finance and all that. So you can see that we have indices and logarithm a lot in many aspects of our lives that are so important. Okay, so let's go ahead and talk about the growth and decay model. So for the growth and decay model, the general formula can be given as A equals A naught into 1 plus R, all raised to power T. This is the general formula for growth and decay. However, so of course here A is final amount. So whether it is money you're talking about, so this also works for compound interest, sort of. Okay, this works for compound interest. This is like final amount. A naught is like initial amount. For compound interest, this would be like the principal. A is the amount, and then of course you have rate, maybe rate of decay, rate of growth, rate of how your money is compounding, and the time it is taking. That is what this is. So R is rate in decimal form. Decimal, so if you have 0.7, that's 7 over 10, right? And T is time. So in some places you see N here, right? This is a general formula for growth and decay model. Now the question is, when do you use this model? You use this model when the quantity changes by a fixed percentage. If at the end of every month your money increases by 2%, or a population increases by a fixed percentage, or it is decreasing by a fixed percentage, you can apply that. So the rate is applied repeatedly over equal time intervals. Yeah, that's the kind of thing I was saying. Whether it's every hour, weekly, daily, monthly, quarterly, whatever, every decade, anyhow, as far as you have a time like that, you have the rate applied repeatedly over equal time intervals, and the quantity changes by a fixed percentage. So you can have examples in population growth, investment. I talked about compound interest, depreciation of an asset, inflation, and things like that. As far as those two conditions are met, fixed percentage repeated over equal time intervals. So example one, we talk about a case of growth, for instance. You have this, that a population starts at 5,000. Maybe when you took interest in the population, the population was 5,000 people, or 5,000 bacteria, or 5,000 whatever. Or even if it is money, you invested 5,000, and it grows, whatever, the population now grows 6% per year. Then find the population after 4 years. So in this case, now you identify the values. The initial amount is 5,000. That's the initial number of uh, population size. Then R This 6% now. So you see, that's why this is decimal. So 6% is 6 over 100. That is 0.06. And the total, the population after 4 years. So T is equal to 4. So step two, now you substitute it to the formula. You know, that's A into A naught equals 1 plus R raised to power 4. So A naught is 5,000. 1 is the 1 here plus R. R is 0.06. 1 plus 0.06 is 1.06. Then 4 is the is the year here. Then you compute that. So you have A into 5,000 multiplied by 1.06 raised to power 4. And you end up getting 631.50. The final answer is approximately, of course, you cannot have half human beings, so to speak. So if you are talking about population or half whatever, so that will be, you have approximately 6,313 people after 4 years if the population is growing at this particular rate. And for some countries that the population is dwindling, we have the idea of decay. But before I go to that, I want to use decimals to compute this. So I have 5,000 into 1.0. So I have 5,000, okay, into 1 plus 0.06, which was already done over the raised power 4. So we have this 6312.3848 like that. But because there's no half human, you just say 6313 roughly, okay? So that's the idea of growth. For decay now, do you know what the difference is? It's all about the rate. So if the rate is positive, that's growth. If the rate is negative, that's decay. So it's the same formula, basically. So, well, and the same rules apply. If the depreciation is consistent over a regular interval of time, then the same thing applies, except that now this is negative. So a car worth $20,000 depreciates 15% per year. Find its value after 3 years. Step one, identify the values. First of all, you have the initial worth of the car, 20,000. Then it depreciates every year at the rate of 15%. That's minus 0.15. 15% is 15 over 100. That's minus 0.15. After 3 years, you want to know the value. So if maybe after 3 years you want to sell the car, you can properly evaluate it based on these parameters. So step two, now you substitute. So again, you have the value after that at that time you are interested in is initial value into one. Now the rate is negative, so you have 1 minus 0.15 raised to power 3. So you have 20,000 into 0.85 raised to power 3. And by the time you compute all that, the final answer is approximately $12,282. So after 3 years, the car has lost it has lost almost 8,000 dollars in value. I mean, it has depreciated by $8,000 over 3 years. So you have 12,282 as the worth of the car at that time. So if you need to sell it, or if you need to do, there's this thing they do, like you take the car to the dealer, and then you pay some money and you get a car, a brand new car. So maybe by the time you take the car back, yeah, the worth is 12,000. So you may need to add some money to get it, but another brand that you may like. You can do that for a phone and things like that, you know. So that's about growth and decay. So the formula is basically the same, except that the rate, if increasing rate is growth, decreasing rate is decay. So then we talk about half-life model. A half-life model, we have that coming up when you talk about radioactivity in chemistry or physics. So the general formula for half-life is something like this. You have A, so you can see it bears a bit of resemblance with that growth and decay model. So, but except for a bit of difference here and there. So you have A to be equal to A naught. That's the initial amount as usual. A is now the remaining amount because it is half-life we're talking about. So you now have half raised to power T over H. Now you see this half raised to power T over H now is more like the what's that thing called? And the initial or exponential part, you know, because half time is now raised to power T over H. So T is time elapsed and H is half-life. Okay. So, based on this formula now, can we do a bit of calculation? Imagine this question right here that you want to do this half-life calculation for a radioactive substance has half-life of 10 years. What that means is that after every 10 years, it loses half, it would have lost half of its value. So if you start with 80 gram, that means after 10 years, it reduces to 40 gram. Okay. Now the question is how much remains after 30 years? So you can follow that idea now. So you identify the values. The initial value, that's the starting value is 80 gram, and then H is 10. That's the half-life is 10 years. and t is 30. That's the time you're taking. So it could be years, it could be whatever, depending on the nature of the substance. Then you can substitute that into the formula, and that is A is initial half raised to power the time all over half-life. Okay, so you then have A equals 80 into half raised to power 3. So that means half raised to power 3 is 1 over 8. So 80 over 8 is 10. So the final answer is after 30 years, 10 grams of the radioactive substance remains. Okay, that's what that is about. Then example 4, we have this other one. It says that okay, this is long, so I can go step by step. So solving for time. So you can see that in this equation of the half-life, there's time here. So what if you know the half-life, you know the initial amount, but you want to now know what time it will take for it to decrease to a particular value, right? So in this case now, you want to find that time. So, but of course, you need to use logarithm here. But, so let's see how that goes. How long will it take for 200 gram to reduce to 25 gram if the half-life is 5 years? So if after 5 years it becomes 100 gram, after another 5 years it becomes 50, and oh, okay, I think I'm already getting where we can do it by intuition, right? If the half-life is 5 years, so after 5 years, 200 gram becomes 100. That's 5 years. In another 5 years, so in that, so 100 becomes 50. That's 10 years, right? In another 5 years, making it up to 15. 50 becomes 25. So that should be 3 years that should be 15 years rather from my intuition. Let's see if the answer is going to tally with that. Okay. So the value we're expecting at the end of at that time we're looking out for is 25. Then the initial value was 200. So you have half response. The t is what we're looking for now, and half-life is 5. So the first thing we want to do here is to divide both sides by 200. So divide both sides by 200. So you have 25 over 200, which is 0.125, and that's equal to half raised per t over 5. Then step 3. So in step 3, we then rewrite we rewrite so we divided by 200, so we got this, right? We are looking for 2. So then we can rewrite 0.125. So 0.125 is like 1 over 8, 0.125 is 1 over 8. So let me see. I think there's a way we can do that here. 0.125. So, okay, so this thing tells you can change it to fraction. If you click on this, it tells you 0.125 is 1 over 8. You want decimal back, just click this 1 over 8. So that's cool. So you can actually take any random value here. Maybe you have 0.0.33333333 in decimal like that. Okay, it's like it's listening. So tells you this is the kind of fraction it is. Okay. So 0.15 is 1 over 8, right? So that 1 over 8 is equal to 1 over 2 raised by 3. So you see, this is us making sure we have a similar base. So in this case now, then on the right hand side, okay, I think I may need to step in here. So I'll take it up from here now. Okay. 0.125 equals 1 over 2 raised by t raised by 5. 0.125 equals half raised by t over 5. Okay. 0.125 equals half raised by t over 5. So what do we need to do? 0.125, we have seen it is 1 over 8, and that is 1 over 2 raised by t over 5. So, and it's clear that we can say this is 1 over 2 raised by 3. That is equal to 1 over 2 raised by t over 5. So now the bases are the same, okay? This base is equal to this base. So we can compare the power. So we know that t now is equal to 3 is equal to t over 5. So we can multiply 3 by 5. So we have 5 times 3 equals t. So it means that it will take 15 years, like I figured. So we have 15 years. So it takes 15 years to reduce to 25 gram. Okay? So it takes 15 years. So t is 15. So final answer is 15 years. So apart from that, we also have the idea of compound interest. Okay, I mean, you can see compound interest is just basically the same thing like growth and decay model. So it's basically just the same, except that here we just call it compound interest. And then we just change so that initial amount the other time is what we call principal. That's the amount you're investing. Then A is whatever you want to get at a particular given time. So you have A equals P into 1 plus RT. So the general formula for annual compounding, this is what you have here. A is final amount, P is principal, R is annual rate in decimal. So if you are given a percentage, take it to decimal. T is years, or it can be quarter or anything. So if it is, so sometimes it can be confused by the timeline. So I can tell you that the interest rate is this particular whatever for, per annum, and then I wanted to find the final amount after 4 months. So you have to be able to do the conversion to be sure that you have a consistent result. So it means you may have to divide the rate by. So in 4 months, that's 12 over 4 months is what percentage, what fraction of a year. That's like one third. So it means that your rate has to be divided by must has to be multiplied by 1/3, or the rate has to be divided by 3, right? So for that to be consistent. Okay, so imagine this now. You want to find a final amount. So invest $3,000 at 8% annually for 5 years. So what's the final amount, right? So you substitute the final amount you're looking for. A is equal to initial amount. There's the principal, which is 3,000, and 8% annually. So it's increasing. So you have 1 plus 0.08. That's 1.08 raised per 5. If you compute all this now, you get 4,408. So it means after 5 years, your investment is now $4,408. Doesn't look like good business. I don't know. It all depends on the context. So here, okay, I guess there's something I can do to make sure this doesn't look this way. So I think I can put a backslash here, and then things get good. Yeah, I think that backslash should help. Is it helping? Is it helping? Is it helping? $2,000, $5,000. Still not helping to grow to. Doesn't seem to be helping. It should actually. I suspect it should help. But it's okay. Whatever. So solving for time now. Okay, we can also solve just like the other time we could solve for time. So when the variable is in the exponent, we use logarithms. So what we did the other time, we didn't have to use logarithm because we're able to say get 1/8 to be half raised per something. So in this case, we may have to use logarithm if we can't get the same base like we did before. So solving for time, how long will it will take? $2,000. 2,000. So it's seeing these dollars as dollar sign for, okay, I guess I can, okay, let's try to see what's happening here. This, what if I double it? This, okay, now that's making sense. Then I have this, yes. So with that, okay, nice. This is looking good. So I can then remove this, and I think it makes sense. Then I remove this. Oh, okay, okay. So let me take it back. Yeah, so let's make do with this then. Okay, now this is fine. Okay, this is looking better. Okay, okay, it's long, so let me do it in steps. So when the variable is in the exponent, we use logarithms. So of course, we have encountered this a lot. So if you can get the same base, you compare exponents. If the bases cannot be the same, you use logarithm. Okay, and of course, we're still going to talk about logarithm because this is indices and logarithm. And we've been talking about indices so far. So solving for time, how long will it take $2,000 to grow to $5,000 at 7% interest? So now we are looking for T. Okay, so step one is substitute. So the amount you are looking forward to is 5,000. So you can actually plan, right? So if you are investing, so you want to know, okay, I need $10 million after 5 years. How much should I invest at this given rate to get it at that time or something like that? So you can use this equation to or this compound interest model to figure all of that out. Okay. Yeah, 5,000 equals 2,000 into 1 plus 0.07. 7% is 0.07. That's 1 plus 0.07, which is 1.07. And T is what you're looking for now. So next, you divide by 2,000, divide both sides by 2,000. So 5,000 divided by 2,000 is 2.5. So, and of course, this is like 5 over 2, but it doesn't look like 1.07 can be 5 over 2, right? So what we then have to do is to take the logarithm, take natural logarithm. So the natural logarithm of 2.5 is equal to natural logarithm of 1.07 raised power t. So t can come down. So you have ln 2.2, ln 2.5 equals t ln 1.07. So you can divide both sides by ln 1.07. So you have t to be ln 2.5 over ln 1.07. So ln 2.5 is approximately 0.9163. Ln 1.07 is approximately 0.06766. So if you put all that together, I get 13.54. So the final answer is approximately 13.5 years. So if you want to grow 2,000 to $2,000 to 5,000 at 7% interest, so it will take 13.5 years. Okay, that looks like a small, the growth is very small, but it's okay. That's the deal. So then this also will also help you to know, okay, if somebody is offering 7% at this, somebody else is offering maybe 7.2%. That's 0.2% can mean a lot if you do the maths, right? So summary of the models we've looked at as exponential models or initial models, if you like. We saw the growth model, which is a equals a naught into 1 plus r raised by t. Decay model is basically like that, except that the rate now is negative. Even compound interest is basically like the growth model too. Exactly the same, except that here, instead of a naught, we use p for principal. Then for half-life model, we have a equals a naught into half raised by t over h. So all these are very lovely applications of exponential or indicial models. All right. So 10.5 tells us common mistakes we need to avoid when we're using exponential models or indicial models, if you like. So using percentages instead of decimals. Okay. Don't use percentages, use decimals instead, okay? So that can be really confusing. So use decimals, not percentages. Then forgetting negative rates for decay. So if there's a decay, you have to use negative rates. That's the basic difference between growth and decay. The positive rate is growth, negative rate is decay. They're mixing time units. Exactly. I think I talked about that. So if you are talking about how, compound interest, maybe you have 7% per annum, okay? 7% per annum. And you now want to know how much your money would have, some amount would have become after 7 years, 3 months. You have to figure out that time thing, okay? Then rounding too early. Don't round until you get to the absolute end of the calculation so that you can get something as accurate as possible. They're not using logarithms correctly when solving for time. Now, that can be a problem too. So we have some practice problems here. As usual, I have 20 of them. So see 10 of them at once. Maybe I'll take one, or maybe I shouldn't take any even. I don't think it's necessary because the formulas are very straightforward. So solve each problem, round answers to two decimal places where appropriate. A population of 8,000 grows at 5% per annum. Find the population after 6 years. Okay. Yeah, these are looking like regular stuff we should be able to handle like that. Okay. So half-life 6 years, mass is this. Yeah, we can figure this out after 18 years. Okay, 11 to 20. Okay, well, maybe all the 20 can even fit. Okay, I think it's better to show it in bits, even if it is not 11, like maybe like 9 to 20. Okay, 7 to 20 is showing. That's fine. So a forest area of 50,000 trees decreases at 4% per year due to disease. How many trees remain after 10 years? Okay, maybe I should just figure this out. A forest area of 50,000 trees. Okay, forest area, 50,000 trees. Okay, that's initial number of trees. Okay. A naught is 50,000 trees. So what else do we have? Then decreases at 4% per year due to disease. Decreases, that's very instructive. It's decreasing. Okay. So we have rate is minus 4 over 100, that's 0.04. It's a decrease. So pay attention to that. It's decreasing. How many trees remain after 10 years? Okay. So we have T to be 10. Okay. And then we need A after that time. So I hope that let's check for time mixture. So 4% per year. Okay, good. After 10 years, so everything is consistent. So now this is actually a kind of a decay model. So we can use that concept. So we know already that A is equal to A naught into 1 plus rate per time. Okay, so we need A now. So that means we just have A into how many trees to start? 50,000 into 1 plus the rate is minus 0.04 and then the time is 10. Okay. So we have A now to be 50,000 into 1 minus 0.4 should be 0.96, I believe. Yeah, 0.96 raised to power 10 now. So that means the number of trees after 10 years will be 50,000 into 0.96 raised to power 10. So Desmos to the rescue, 50,000. Okay, so now here I have 50,000. Oh, well, there was a 55,000 here, so I just said 50,000 into 1 minus 0.04 raised to power 10. Raised to power 10. So that's 33,241.6. That's roughly 33,242. 33242, right? 33242. 33242. Okay. So there are 300, roughly 33,242 trees after 10 years. So that's the decay. So if you want to rescue the forest, you know what to do to reverse. Maybe there's a way you can actually mitigate the effect of that disease so that it doesn't have all that impact. Okay. So that's the kind of thing we have here for solving exponential models. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you have not subscribed, please go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges like getting to see some videos first or be the only one to see certain videos. And apart from that, we can also hang out to discuss anything that interests you on my channel, be it mathematics, be it machine learning, data science, data analysis, Python programming, scholarships, whatever interests you here. We can hang out to discuss them physically or online. Physically, if you're in the same location at any point in time. Online, also, if you're not, or I mean, if that's your option. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.